We had seen a bell-like curve make a rather mysterious appearance when we looked at the binomial. And naturally, to get a just understanding of where this phenomenon comes up, we should return to that most elementary of settings, the toss of a coin. So let us go back and consider the repeated tosses of a fair coin. We're considering a situation where we have symmetric Bernoulli trials, in other words, fair coin flips. As always, we will denote the successes by ones, failures by zeros, and we have an independent sequence of ones and zeros that we label x1, x2, x3, xn, and so forth. In our notation, these connote symmetric Bernoulli trials or Bernoulli trials with success probability p equal to 1/2. Naturally, we form accumulated sums, and once we form the accumulated successes over n trials, we get what we call S subscript n, or simply Sn, as a sum of the first n x's. Sn denotes the number of successes in n tosses of a fair coin. And of course, we know now that this is governed by a binomial distribution with two parameters, n, the number of trials, and the success probability, which in this case is 1/2. We have a discrete setting, and of course it's completely characterized by a mass function. The mass function attaches to atoms the atomic probabilities that we called b sub n of k with the parameter little p, which in this case again is 1/2, and so the binomial probabilities simplify in form. They are of the form n choose k times 2 to the power minus n, and k runs through the possibilities for the number of successes 0, 1, 2, 3 up till n. We know that this distribution has a center of mass, an expectation exactly at n over 2, and a variance as n over 4. By now we have a fairly good understanding of this most basic of objects, the binomial. The question at hand is, how does this distribution behave as n marches on and becomes larger and larger and larger? And so here are a couple of pictures. So we look at a sequence of values, n is 10, 25, 50, and 100. And as you can see, the distribution marches on to the right, getting increasingly spread out and more congested. And already certain interesting features are beginning to become apparent. But one of the things we will promptly need to do is to find some mechanism for comparing all these different distributions for different values of n, all under the same framework. So let's take a look at this picture again, and this time realize that what characterizes each of these distributions is its expected value, which is growing with n as n over 2, and the variance. Yes, assuredly, as n increases, the distribution is getting more and more and more spread out. But the spread, as we've seen, is small compared to how far the expectation is moving. A natural way to characterize this is first to center the distribution at its center, in other words, at n over 2, and look at it in a proper scale, in other words, by dividing by the standard deviation. So let's introduce a new variable. For every value n, let Sn star denote Sn centered at the origin by subtracting its expected value, and then normalized to a unit spread by dividing by its standard deviation. What we've really done is taken the accumulated successes and made them dimensionless, centered and dimensionless. Of course, we realize that here the expectation of Sn is exactly n over 2, and the variance is n over 4. And so our expression becomes Sn minus n over 2 divided by, in the denominator, 1/2 of the square root of n. Here is a new chance variable, and as n increases, we get a sequence of chance variables. Of course, each of these variables is inherited from S sub n, and therefore inherits the binomial distribution, except that it's going to be recentered and rescaled. So the axis is going to be scaled to have it, at least the spread, to be unit. What does the mass function of this standardized scaled variable look like? Now, Sn star, a properly centered and scaled version of Sn, is itself a discrete variable. It is now centered at 0, so the values Sn star takes are scattered around the origin. The spread is normalized to unit, so each of the Sn stars is spread essentially the same range. At least most of the probability lies within, say, 2 or 3 units of the origin. But it is still a discrete variable, and it inherits its mass function entirely from Sn. In other words, each of the curves you see is going to then get rescaled and moved to form the mass function for Sn star. Let's take a quick look at it. Right. So, starting on the screen from the upper left, clockwise all the way down, you see at n equal to 10, n equal to 25, n equal to 50, and n equal to 100, these recentered, rescaled mass functions. Does anything leap out at you? Indeed, it does. These functions all look remarkably similar, taking into account, of course, the fact that as n increases, Sn star has got more and more points, places where it takes values. But the mass function, if interpolated through, is beginning to look more and more like a bell curve. Now, to be sure, there is a vertical normalization to be taken account of. And this arises because as n increases, there are more and more points where Sn, and therefore Sn star, takes values, and therefore the probability masses are getting more and more spread out, and therefore the heights of the probabilities are decreasing. But, properly normalized, it does appear that the curves are looking increasingly bell-like. And this leads to a powerful and potent and speculative idea that it just may be possible to compute binomial probabilities approximately by areas under a bell curve.